Could it be that everything we know about the universe boils down to just one thing, time? Physicists are challenging the very foundation of our understanding of the cosmos, suggesting that all those seemingly fundamental constants we rely on might just be different facets of a single, universal yardstick. Prepare to have your mind blown. In the hallowed halls of CERN, back in 1992, a simple cafeteria conversation sparked a debate that's still raging today. Three brilliant physicists, Michael J. Duff, Lev B. Okun, and Gabriele Veneziano, found themselves at odds. The question: how many fundamental constants do we really need to describe the entirety of nature? You've probably heard about these constants. They're the seemingly unchangeable numbers that underpin our understanding of physics. Think of the speed of light, Planck's constant, crucial for quantum mechanics, and the fine structure constant, the source of much head-scratching among physicists. These are physical quantities that can't be derived from theory alone, we have to go out and measure them. As Martin Rees, Emeritus Professor of Cosmology and Astrophysics at the University of Cambridge, puts it, these constants are the fixed quantities in nature, such as the gravitational constant, called g, or the speed of light, called c. He notes that there are roughly 30 of these, representing everything from particle masses to the strength of forces and the universe's expansion rate. And here's where it gets controversial. Our existing theories don't explain why these constants have the values they do. We simply measure them and plug them into our equations. But how many of these constants are absolutely necessary? That's the question that's been bugging physicists for decades. The International System of Units currently uses 7 base units: seconds, meters, kilograms, amperes, kelvins, moles, and candela. But a recent paper throws a curveball, suggesting that we might only need one, time. The conversation that started in that CERN cafeteria led to 3 separate papers published in 2002, each proposing a different answer. Okun argued for 3 fundamental units: length, mass, and time. Veneziano thought 2 were sufficient: length and time. Duff, however, believed that the required number of constants depended on the specific theoretical model being used. The goal is to find the most fundamental description of physics possible, explains George Matzes, the lead author of the new paper. The question raised by Okun, Duff and Veneziano is by no means trivial. As physicists, we're faced with the need to understand what's the minimum number of standards we need to measure everything. In their recent work, Matzes and his team delved into how many constants are needed to describe 2 different types of spacetime: Galilean spacetime, used by Isaac Newton, and Minkowski spacetime, used in Einstein's theory of relativity. In Galilean spacetime, space and time are distinct entities. Time is absolute, meaning everyone agrees on it, and distances are independent of time. You can't derive one from the other. The authors argue that in this framework, other units like mass can be defined using just these 2 constants, length and time. And this is the part most people miss. When they turned their attention to Minkowski spacetime, which they believe is applicable to relativistic spacetime in general, they arrived at a startling conclusion: you don't even need length. In Galilean spacetime, you need rulers and clocks to measure all the physical variables. In relativistic spacetime, however, clocks are sufficient, Matzes explains. The key is that in relativity, space and time are intertwined. Because in relativity, space and time are not independent, one can be derived from the other. This is because in relativity, space and time are so interrelated that a single unit is sufficient to describe all quantities. High-precision clocks, such as the atomic clocks used today, are capable of meeting all measurement needs. To demonstrate this, they invoke a thought experiment proposed by Canadian physicist Bill Unruh. Imagine 2 observers, one with 2 synchronized clocks and the other with just one, positioned at opposite ends of a rod they want to measure. The observer with 2 clocks sends one to the second observer, who synchronizes his clock to the received clock. The clock is then sent back. Because time is relative in relativistic spacetime, affected by velocity, these time measurements can be used to define length without relying on the speed of light or any other constant. In essence, the team proposes that everything can be measured using just one constant, the second. The second is currently defined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Now, before you start throwing out your rulers and scales, it's important to remember that this doesn't mean other constants are useless. They're still incredibly convenient. As Daniel Vanzella, from the São Carlos Institute of Physics at the University of São Paulo, points out, having a mass standard is practical, even if it's not fundamentally necessary. He explains, the mass of a body is given by the acceleration with which a particle is attracted when it's at a certain distance from the mass. Historically, mass was defined based on the mass of water, which is a good example of how constants have been created out of convenience. So, what does this all mean? Could it be that the universe is simpler than we thought, governed by a single, all-encompassing constant? It's a mind-bending idea that challenges our fundamental assumptions about reality. But here's the kicker, does this simplification truly advance our understanding, or does it merely shift the complexity elsewhere? Does focusing solely on time obscure other crucial relationships between physical quantities? And what are the philosophical implications of a universe ultimately defined by a single, ticking clock? Let us know what you think in the comments below.